thank you guys for sticking it out to the end. I don't think there's anything really important going on this afternoon, so I appreciate every one of you being here just for me. So I'm going to finish up today with two topics. So I want to continue talking about multicellular sensing. And then I also want to say a few words about the thermodynamics of sensing, because that is a very active research topic these days. And it addresses the fact that we've thought a lot about what constraints the environment puts and what are the limits a cell can do, but we haven't talked about the costs that are incurred by a cell doing the best that it can. So in the context of the multicellular stuff, so yesterday I talked to you about how cells can use communication to improve the precision with which they sense a background concentration. Today I want to talk about sensing not a background concentration but a gradient in a concentration field. And I want to start by telling you a story. So this is a story, not a parable, because it's my own work. And it's work that I started when I was a postdoc with Ilya. And we were collaborating with two experimental groups, the labs of Andrei Levchenko and Andy Awald. And we were looking at particular cells, epithelial cells, that form a particular structure inside of mice. So what we did is, now I'm a theorist, as you know by now, and so when I say we in this project, I don't mean me. But what Andy Awald did is he took a mouse and, here we go, and extracted an organ and chopped it up, basically. So we were interested in only a part of this mouse, and certainly not its behavior. And that part is essentially the mammary gland of the mouse, made up of these ducts that transport milk. And so, one of these ducts is made up of, it's a tube, it's a tubular structure. It's made up of sort of this layer of epithelial cells, and it transports things through this duct. And these ducts have a particular morphology, and that morphology is, is actively forming when the mouse is developing as, from the stage of an embryo, for example, but also when it undergoes hormonal changes, like when it gets pregnant, right? And it needs to sort of set all this new structure up. And so one of the stages that you might find these ducts in is when it's sort of not fully formed yet, and it's sort of growing, and it has this group of cells, epithelial cells on the end of it, which is commonly referred to as an end bud. And it's generally assumed that this group of cells is sort of sensing factors in the environment and determining where and how far that duct will grow. And these were the cells that we were interested in because, we knew some things about them. We knew that they sense growth factors, and we know that they sort of respond in a, using a morphological and motility response to those growth factors. So, but we wanted to study these cells in a more controlled environment, and so when I say that Andy chopped them up, I mean that, we sort of, chopped them up and put them inside of a very controlled chamber that just basically had collagen in it. And what happens is that they stay mostly intact, but they kind of close off. And so instead of a cylindrical duct-like shape, they form a sort of hollow sphere-type shape, except that sphere is still soft and can have different sort of morphological properties. And generally speaking, when you take any organ out of a living being and you chop it up and you look at it in isolation, then people call it an organoid. It's not quite an organ anymore, but you hope that it retains some of the properties, at least the ones that you care about. Now, the advantage of this is that we could, run fluid channels on either side of this chamber and send epidermal growth factor through one and then just, regular medium through the other, and that set up a gradient just by diffusion. That set up a gradient of this growth factor attractant along the chamber. Right, so the goal was to investigate what this group of cells does in response. And by the way, we could also tune the degree to which single cells sort of pinched off from this organoid. And so we could also watch the response of single cells as well. So what we saw is that if you have a strong gradient of epidermal growth factor, which specifically is 50 nanomolar per millimeter in our experiments, and you look at the behavior of a single cell, then it wiggles around through the collagen in a biased way. Okay, it executes a biased random walk. But if you reduce, and this was known before, I mean, these are cells that, whose gradient tracking properties had been studied before. If you reduce the gradient by a factor of 100, to 0.5 nanomolar per millimeter, then the single cells will still move around, but they'll just do an unbiased random walk. Okay? So this was important for us to establish sort of the threshold below which a single cell could not detect the gradient. But in the same weak gradient, you can watch the behavior of the organoid. And what it does is it's a very active thing, and it sort of forms these protrusions, these multicellular sort of branches on all sides of its body. And in the presence of this weak gradient, we saw that it was basically biasing the branch formation toward the high concentration side. Okay? So this was sort of the sweet spot, a regime where single cells can't really detect the gradient, but when they're in a group, they can. And this is the way that they were sort of reporting that to us as a bias in the angle of the branching. And then in order to try and get a little bit of information about how this was happening, what Andrei Levchenko did is he basically perfused in one of several drugs that are known to block the gap junctions between cells. And when we put those drugs in, then the organoid still branched like this, but the bias went away. Okay? So, gap junctions are basically these channels that allow molecules to flow across the membranes of two adjacent cells, and when we block that, then we block the branching bias. Okay, so that told us that however this system is doing this behavior, doing what a single part of it cannot, is reliant in some way on the ability of the cells to communicate. So this was sort of the set of data that got me interested in understanding how cells can work together to sense things in their environment. And it raised basically two questions. One is, how is it possible that the multicellular system is sensing what the single cell cannot? And what is the role of communication in this process? So the first question, how can the organoid detect what single cell cannot, I think we can understand using the same sort of rough arguments that we've been developing along the lines of Berg and Purcell. Right? So the basic intuition is that the organoid is bigger. Okay? So it covers more of the gradient. It should be able to detect shallower gradients than something that covers a smaller size. And we can make that precise, right? So if you remember, our result from the precision with which a single cell can detect a gradient, we came up with an expression that looked like this. So I can call this, as I have been, the squared error, where I'm defining it as the variance in a single cell's estimate of the gradient over the mean of that estimate of the gradient. And whatever mechanism you look at, you find an expression that looks like C naught over a cubed g squared dt. Right? This was the expression where we needed to sort of discuss why the C naught was on the top, and that's because the gradient detection is essentially a subtraction, and it's harder to do a subtraction on top of a large background than on top of a small background. And I want to break this expression up just a little bit to remind you of its origin. So I'm going to write this as C naught over a dt times the quantity ag squared. And the reason I write it like this is because this a, when it multiplies the g, comes from or came from the extent over which the sensor is spread, right? That's a times g. That's sort of the difference in concentration from left to right. And this a comes from the size of the detector that's actually doing the detecting. Okay? Now, the reason it's important to separate that is because when we have a collection of cells in an organoid like this, then those two things, these two A's can be different, right? They have different physical origins, and we need to be careful, is my point. So if we try and write down the analog of this expression for a multicellular system, then we can imagine an organoid like this, and let's say, we have cells. I'm not going to draw them all, but we have, cells that make this up. And it has a certain extent, right? It covers a certain distance of the gradient, which I can call capital A. But the things doing the detecting are the individual cells, right? So this I'm still going to give a length scale little a. And so what we would expect for the precision of gradient sensing here would be something like the background concentration over little a dt, because once again, this comes from the size of the detector, how many molecules you can count, times big A g quantity squared. Okay? And if I want to think about this in terms of precision, instead of error, I can define precision as 1 over the error, for example. And this will then look like A times g times the square root of little a dt over C naught. Right? So the point is that we should expect indeed that the precision with which something can sense a gradient should go up with how big it is, right? And in fact, we should expect specifically under this definition that it should go up linearly. Right? Okay. So that's sort of like, to 0th order, how we might explain the fact that a bigger object can detect something that a smaller object cannot, right? Because the precision goes up with the size of the object. But this doesn't account for the final experimental observation, which is that whatever this is doing relies on communication. And so what we wanted to do was sort of understand more deeply how communication is involved in this system and whether or not that changes the expectation that I've outlined here. Okay? And there's sort of a more fundamental reason why we were interested in this problem, and that's because it's sort of a general task. If you have many sensors distributed over space and they want to do some sort of collective computation, it's a general question of how they should do that, right? What's the mechanism? So, we don't have to think about cells to think about that, right? So if we're in this room, right, and we want to know, where we should go to find some delicious food or something, right? Then, it may not be possible for any one of us to stand here and know if I smell an apple pie or something, what direction it's coming from, right? So let's say I'm in that situation, right? I just smell a pie and I can't figure out where it's coming from. What might I do? One thing I might do is try to navigate, right? I start moving around just like the amoeba, and as Massimo is mentioning, I'm changing my environment and maybe I'm improving my ability to gather statistics, right? That's an individual action, right? But what might I do to take advantage of some sort of collective computation? I might ask somebody. And I'm losing my voice, so I might just ask somebody closest to me, and I say, do you smell pie? Right? And, maybe if I'm standing in the middle, I say, do you smell pie? No. Do you smell pie? No. Do you smell pie? Yes. Oh, okay. Could you ask some other people and see whether they smell pie, right? And we can sort of start to zero in on the direction of the gradient, right? But the point is that, it's a relay, right? I can only ask a neighbor under the assumptions of how we think these cells are communicating. And that information has to sort of go out and it has to come back, right? And it has to be sort of processed and compared to, my own measurement, right? I can't forget that I didn't smell pie once I acquire all the information through this relay and it comes back. And I should also know that anyway. So this is a general problem. What kind of mechanism do you use to collectively gather gradient information, and how can it be encoded in sort of the internal network of a cell? And so I hope that it's clear from my silly example that what you're essentially trying to do is take your local measurement, which is not good enough, mine being I didn't smell pie, and somehow compare it to the information that goes out and comes back, some sort of global measurement that's obtained by a relay. And that's what I was saying yesterday, that a gradient is sort of a vector. It's magnitude and direction. So you need two things, and those are the two things I'm suggesting, a local measurement and a global measurement. And in particular, those are the things I want to subtract, right? So how can I encode that in a sort of cell signaling model? So we thought about that and we came up with the simplest possible thing, basically. I mean, it's true that some features of the intracellular signaling pathways of this cell are known, but we wanted to sort of be agnostic to that and at least start with something that's minimal to achieve the task that I outlined. And so that was the following. So we have these sort of two cells that I drew. We imagined, we later extended this to sort of a full 3D thing, but we started by just imagining the sort of belt, the waistline of this organoid, and the cells that go from one end to the other. And this is the important cell, by the way, in this model, right? This is the cell that's asking, should I branch? Right? And, so basically in the model there's less epidermal growth factors on one side than there are on the other. So let's say there's a lot over here and less as you go to the left. And we imagined, as I was talking about last time, that each cell has receptors, etc., and molecules can bind receptors, and bound receptors can produce some internal messenger molecule as we had before, and that can be exchanged among cells. Okay? And it can be degraded, right? Very similar to the sort of short-range communication model that we discussed yesterday. This, however, fulfills only one of those criteria, right? This short-range communication is sort of taking all of the measurements made by each of these cells, and it's communicating them along the chain, right? This is the analog of doing the relay, as I was describing, right? So this I would call the global measurement, right? So we have a sort of background concentration that is, a linear profile, for example. We have R, which is the number of bound receptors from before. We have M, which is the amount of internal messenger molecule. And M is what I would call the global measurement. So we realized that really the only thing we needed to add to this model, aside from the graded concentration, is some local measurement. And the only difference between the global and the local measurement is that the local measurement doesn't get exchanged. So we imagine that there's some other molecule that gets produced, which I call, the number of which in cell I can call N. And it gets produced and degraded just like the global molecule, except it does not get exchanged, right? So that's like my local information about what I detect. And so we wrote down the same sort of Langevin style model that we did before, right? So we have a diffusion term for C. We have sources and sinks from each of the cell locations because of receptor binding. Say we have N cells in this chain. We have to prescribe where these cells are. We assume that they're going to be in a chain. The dynamics of the receptor binding give the sources and sinks. There's noise. Receptors bind with propensity alpha times the concentration at that cell of the epidermal growth factor. They unbind. We're again neglecting receptor saturation. And then we have the sort of short-range version of the diffusion term for this global signal M. Right? It's just sort of like a discrete Laplacian operator to describe the exchange. And in this case, it is just one-dimensional discrete diffusion. Right? So this is neighbor on the right, neighbor on the left, and then molecules that leave that cell, right? Plus some noise term. And then this N has this exact same dynamics as M, except without the exchange. So it has some slightly simpler noise term, right? So I won't belabor the process. The calculation is the same. The noise terms have the appropriate statistics. And the boundary conditions enforce that this is now a graded signal on average instead of a uniform signal on average. And like I said, the key quantity here that we were interested in is for this N cell, right? So I equals 1, 2, etc., all the way up to cell N. The question of should I branch, right? And as I was mentioning, this is really a subtraction, right? This is a question of whether or not the local measurement is higher or lower than the global measurement, right? So we defined an observable which was in cell N simply equal to N in that cell minus M in that cell. Okay? And there's many ways for a cell to do this, by the way. So the other thing that I'm sort of glossing over is how a cell even does a subtraction using an internal signaling network. And you can have basically N and M antagonistically produce and degrade some third species, right? And then the production one would be N and the degradation one would be M, and so it's sort of like an antagonistic tug of war, and that essentially encodes a subtraction in the appropriate limit if you're near saturation of that third thing, for example. But that's not the only way. The point is that there are sort of simple networks you can imagine that will do this kind of computation. Okay, and so we're interested in the statistics of this quantity, and in particular, to sort of think along the same lines as I drew there, we're... Yeah.
Some of the other things that were mentioned here, maybe not mentioned. Right? When we talk about, for example, Drosophila developing this egg that people saw around and so on, there is this old work by Turing, right, 60, 70 years ago on global excitation, local inhibition, right, which is what forms patterns in development and so on and so forth. And essentially, this is also what this is. This is global excitation, local inhibition, local signal that drives you up, global signal average, which is suppressed, right? And so this type of motifs are apparently everywhere in biology, in every corner, and many different ways of realizing them. It's not that Andrew something created here that didn't exist before. Right?
Yeah, exactly. So I am far from the only one thinking about this problem, absolutely. And in fact, this is exactly how people, including our collaborator, Andre, have been thinking for a long time about how a single cell detects a gradient, right? So I was mentioning when I was talking about single cells that in order to, compare receptors on one side of your cell and the other, there needs to be some sort of internal global signal, which is a diffusible molecule, for example. And the mechanism is very much the same. So all we're doing here is essentially implementing such a mechanism in a multicellular context. So good. So if I care about then the precision of estimating this statistic, then I simply need to calculate its mean over the variant, or the standard deviation, for example, of its long-time average. Okay? And so we do that, and it has a particular form. I'm not going to write it down, but I am going to sort of illustrate what we find when we plot it, for example, as a function of the size of the system, which here is just the size of an individual cell times the number of cells in the chain, right, roughly speaking. So what we see is the following. We see that it increases as we would expect, and then it does something like this. It saturates. Any ideas on why it saturates? Or any ideas on what sets the size at which it saturates? So let's think about what this is saying, right? It's saying as the collective of cells gets larger and larger, I learn with higher and higher precision about the gradient up to a point. So I can put that another way. As the size of my summer school gets larger and larger and larger, I learn very well where this pi is up to a point. If it gets to, what are we this morning? 40 maybe? Then I have a good idea of where the pi is. If we get to 100, I have an even better idea. If we get to 1,000, I'm actually not doing much better than 100. Why is that? Yeah. Wrong. No, what? What if there is no pi? So I don't understand the question. That's my whole premise.
But there is no pi. In fact, in the situation, so it doesn't matter how many people we have in the room.
It doesn't matter.
How many people you have in the room.
Okay, if g goes to 0, I should expect this to go to 0. That's certainly true of this expression. So this obeys, and you'll have to trust me that it's also true of this expression. Right? I've drawn this for a finite g. Mike?
So it's not like you're going to be able to like exchange molecules between like the ones at the very front and the very end. Like there's like characteristic length scale for this diffusion because it's degraded.
Absolutely. There's a characteristic length scale for this diffusion. That's like saying there's a characteristic length scale for information gathering among the students of a summer school, right? In the summer school, this is very much like the game of telephone, where you're passing messages and then they come back and they get distorted, right? If you passed it among 1,000 people, a yes might turn into a no for some reason. Here the noise comes from the intrinsic low numbers of molecules, for example, which is, molecule numbers are essentially set by ratios of rates, and in particular, the intrinsic diffusive length scale is set by the ratio of the exchange rate to essentially what sets the time scale for this process, which is the degradation rate of the exchanged molecule. So indeed, this is a certain effective size, which I'll call A times N naught, and N naught is actually the square root of the exchange rate over the degradation rate. Right? So it's the square root. It's very similar to the exponential diffusion profiles that we were seeing yesterday, where the length scale is set by the square root of diffusion over the degradation rate. Right? Gamma here is playing the role of diffusion. And indeed, so if there's a finite rate of communication, then there's a finite length over which you can gain information. Moreover, we can also ask what is the saturation point, and we see what we expect to see, which is that this saturation point has the value of essentially the sensory capability, the sensory precision of a system that is of this effective size, right? So this looks like A and not G square root of A dt over C naught. Right, so the intuition is that the precision is only as good as some subsize, some subunit within the organoid for which communication is not corrupted. Yeah?
Their precision is about the delta n, which is the difference between n and n. And I don't understand why the difference between n and n has anything to do with the precision of the measurement of the concentration.
Of the gradient?
Yeah.
Yeah. So the question is, why does the difference between n and m have anything to do with the measurement of the gradient? So the answer is that n is giving just the local readout. So n is a readout of the local amount of the chemical, the signal. M is giving a measure of some sort of average between the local readout and nearby cells' local readouts, right? So now imagine that the signal is highest over here. This cell's local readout will be high. This cell's local readout will be slightly less high, slightly less, slightly less, slightly less. But then M is the average of all of those measurements together, okay? So now this cell knows that it has a high N, but a slightly less high M because it's been averaged with smaller values. So by subtracting its N from its M and getting a positive number, it will know that it is reading out something that is higher than its local neighbors. And if it's reading out something that's higher than its local neighbors, that means that it's at the high end, not the low end of the graded signal. Does that make sense? Okay. That's what I mean by doing a subtraction. Okay, so the question is this actually how it goes in the experiments, right? So we subdivided the organoids into different size categories, size bins, and we compared this prediction with the data. And actually, to do that, we calculated the sort of branching bias, right? So we calculated an order parameter from 0 to 1 that was 1 if it was totally, all the branches were in theta equals 0 direction, and it was 0.5 if it was isotropic. So that's just a monotonic relationship with this precision variable. So this is also how the bias looks. And when we compare to the data, we see something like the following. So single cells can't do anything. The smallest organoids can do something. And then it gets pretty messy. This is a nice thing about like not actually showing you the data but drawing it, right? You have to trust me of how good it is. But I do want to sort of do it justice because you can always Google this paper, and I don't want to lie to you. But it's not great. But all we were really interested in here was whether or not it looked like it was continuing to increase, or it looked like it was saturating. And that's something we could actually tell quantitatively from the data, that it did saturate. And more than that, we could actually infer from the statistics a value of this effective length scale at which it saturates. And that effective length scale corresponded to about 3 to 4 cell diameters. So what does that imply? That implies that essentially, the cell that's sort of initiating the branching really only knows information from about 3 or 4 cells back, not the entire object, right? So it's an implication about how far cells can reliably communicate within this object. And there are a couple ways that you can ask whether or not this is reasonable. Yes, Gordon?
It's not necessarily that they only know information from 3 or 4 cells back. It's because it could be that information from way back is transmitted through all of those cells, right? So if there was no information here, imagine like I had like a very flat gradient, and all of a sudden it was really
Oh, I
big.
see.
So it could theoretically have information from way down the line, but
Yeah, that's true. So is what you're saying that, there could be only really valuable information from this cell, but along the way there's noise, and so the quality of information that gets to the cell is as if it came, from nearby. But yeah, okay. That's
feasible, or is that just
well, I guess to ask that we would just simply need to change the mean C profile, and then sort of what I would expect is that we would get an effective size that would map, what the equivalent would be if it were a nice linear profile. Yeah. Yeah, but I mean, I think the qualitative result would remain the same, right? The farther that, valuable cell is, the worse the information. Yeah. So the way we interpreted it was a couple ways, right? So, we went back to the sort of natural anatomy of this duct, and the width of the portion that we sort of presumed was doing the gradient sensing is not much more than 5 cells, right? So this was at least consistent with, the natural morphology of the thing, in the sense that, it's that end bud that we think is doing the sensing. But the other thing we did is we did subsequent experiments where we actually tried to learn something about what these N and M molecules were, right? What is being blocked when we block the gap junctions, right? That would be a candidate for this global M molecule. And so you can do something a bit more specific than blocking the gap junctions and then preventing all communication. You can actually block particular molecules from actually being produced. And if they're the communicator, then you should see the branching go away. And that's what we saw when we prevented calcium from being released, right? So that implied that it was either calcium or some second messenger involved in calcium signaling that might be this global communicator molecule. And so you can tag calcium, and you can sort of watch the amount of calcium released by these cells, when you don't block it anymore, as this branching process is going on. And we did not see sort of correlated puffs of calcium for more than a few cells, right? So that was also consistent with this relatively short length scale. It's not like we saw sort of a calcium wave stretch from one side of the object to the other, for example. So those two things sort of told us that this was a reasonable number that was consistent with what we observed. So, okay. There's many other questions that you could imagine thinking about in terms of collective sensing and how cells might coordinate in order to detect their environment. These are things that I'm thinking about along with members of my group, and we can talk about them if you're interested in them. But what I thought I would do for just the last part is, as I mentioned, talk about what kind of thermodynamic costs are incurred by cells in order to do these precise measurements. We've talked a lot about fundamental limits, but we haven't talked about what kind of energy a cell needs to expend in order to achieve these limits. So, any questions before I go on? Okay. So I want to spend a little time talking about the thermodynamics of cell sensing. It will turn out that sensing is a fundamentally non-equilibrium process, and so this is a topic that is sort of interesting beyond the context of cells and sensing, because it's sort of infringes or joins with the topic of non-equilibrium thermodynamics in general and how that plays out in the context of signaling networks inside of cells. Yeah?
So I was thinking about the length of scale that you referred to, the visa.
Yes.
But so this is, I guess this only restricts the communication, even if you assume like that Gordon's idea is not the case, and you can only communicate to like unified cells. So this still allows for global transfer, like if you actually also consider the geometry of the multicellular structure, right? So you can imagine that I have like an arc, let's say. So it's like this, cells are here, and nonetheless they're able to communicate.
Yeah, exactly. So, yeah, one of the things I mentioned is that this is a one-dimensional model, and that's not really appropriate for this three-dimensional object or this three-dimensional shell-like object. And so one of the things we did is we asked whether or not things change if we look at not a one-dimensional chain, but a two-dimensional sheet or a three-dimensional blob or an ellipsoid or something like that. And there were some things we expected, and there were some things that we were surprised at. For example, if you have a two-dimensional sheet and the gradient is in one direction, then you expect that in the gradient direction, this sort of mechanism will work as I'm describing it in one dimension, but perpendicular to the gradient, the value of exchanging molecules there should be good as well, right? Because it's sort of helping this cell is sort of being helped by other cells that are measuring the same signal, right? So the weird thing is that's fine. That's absolutely true for concentration sensing. And it's also true if you want to sense the concentration in a graded profile, right? Which is sort of the task in morphogenesis. But if you want to sense a gradient, you really want to sense a subtraction, then there are cases where the extra dimensionality doesn't necessarily help. And I think it's subtle to get into why that is, but we can talk about that afterwards. Yeah. So the shape sometimes matters. We also thought of an extension where, maybe the local molecule N is also exchanged a little bit. Not as much as the global molecule, but maybe it can benefit from some exchange to reduce its noise, but not at the expense of reducing its signal, because its signal needs to stay different from the other cells. And this is similar to the hypothesis, about the fly embryo. You want to communicate a little bit, but you don't want to wash out the signal. So anyway, there's extensions that we thought about, and we can talk about them. Yeah. Okay. All right, so thermodynamics of cell sensing. So I'm going to do two things. I'm going to sort of talk about two examples that demonstrate, hopefully to you, that sensing something requires driving a system out of equilibrium. And the first, I just want to mention it briefly because I don't know. I know Michael mentioned it, but you guys are familiar with kinetic proofreading? Yes? Has it been discussed in this school? Okay. I know you're familiar. It might be a review. I just want to sort of very briefly touch upon it to establish something that will become relevant in the sort of more modern example of sensing a concentration. So, right, arguably it's sort of the oldest and most classic demonstration of the fact that you can improve the precision in a measurement by expending energy. And it was demonstrated by Hopfield in 1974, and I'm going to just present a sort of minimal, simplified rendition of what he showed. Right. So the basic idea of kinetic proofreading is you have some substrate that is involved in an enzymatic reaction. So you guys are very familiar with this, I'm sure. You have it bind, form a complex, and then that forms a product P. Right. So we can give this a forward rate, a backward rate, sort of velocity rate of product formation V. And the rate of product formation depends on the concentration of the complex, and the dynamics of the complex concentration are given by the rates in this problem, right? So we have F times X times E minus B plus V quantity times C, right? And I'm going to assume that the binding and unbinding rates are fast, that they're faster in particular than the product formation rate. So I'm going to neglect this V. And also, because these rates are fast, I'm going to assume that the dynamics of the complex are quasi-steady state. This allows me to solve for C, and lo and behold, I have the rate of product formation. Right? So this says that this is Fxe V over B. And I'm going to identify B over F as the dissociation rate associated with this binding reaction, right? So this is just XeV over K, the dissociation rate. Now, the idea is, well, the task, let's say, in kinetic proofreading is that X is the right substrate, and we want to think about the error or precision involved in the decision of choosing X instead of a wrong substrate, which I'm going to call Y, right? So if we have an incorrect binding event, to the enzyme of Y, and let's say that happens with a rate F tilde and unbinds with a rate B tilde, forms a complex C tilde, and that forms a product P. I mean, we can be general. I'll just assume that the binding and unbinding is where Y is discriminated. In fact, I'll be even more general and assume that it's just the unbinding where it's discriminated. You can think of this as two things coming together, and the binding would just be limited by diffusion, but the amount of time that the things stay bound will be higher if they have the higher affinity, and so that's dictated by the off rate. This was the same assumption made by Hopfield. Then in that case, we get a very similar expression, but for the wrong product, right? P tilde dot is YEV over K tilde. So K is B over F, K tilde is B tilde over F, right? And if we assume that the amount of X and the amount of Y are the same, that that's not why they're being discriminated, then we get that we can define the error as the number of failures over the total number of events. And if failure is supposed to be rare, then this is the number of successes over the, plus the number of failures. So this is approximately the number of failures over the number of successes. And that's the same as the rate of success over the rate of failure, right? So this is P dot over P tilde dot, which is nothing more than K tilde, K over K tilde. Yes. Okay. So this is all well and good. The insight that Hopfield had is that if there's an extra step, and it's an irreversible step, then this error can be reduced, right? So he said, let's imagine after forming our complex, we have some conformational change, let's say. So our complex changes in some way. And that's necessary in order to make the product. Right? So now I have some new rate W, and other than that, everything else is the same. And let's imagine that just like the complex can unbind, the conformationally changed complex can also unbind. And I'm going to assume that this is the same rate B. That's not necessary, but it's just going to make our lives easier and demonstrate the main point. So the point is that you can calculate the same quantity with this new model, and you get a W in there, and you get a B squared. Okay, and you can calculate the same thing for the incorrect binding of Y to the enzyme, and you get the same thing, but with B tilde squared. And if again you assume that X and Y are of the same amount, then you find that your error is squared. Okay? So roughly speaking, this extra reaction step has reduced your error by itself, right? Your error is something less than 1, you square it, you get something less. And the point that I want to make here is that irreversible reactions are fundamentally non-equilibrium, and it's because this reaction is irreversible that this works. Okay? You can see that very immediately by imagining that instead we introduced a reaction that was reversible, right? So now if we had a W here and some other rate Z, let's say, and then similarly, instead of an irreversible reaction here, we had a reversible reaction as well. So let's say in addition to B, we had a forward reaction as well. Once again, if it's diffusion limited, we can assume that that's the same rate F. That's not necessary either. I'm just sort of making this easy to show the main result. Now, if these things are reversible, then what we have here is essentially a triangle, right? A set of reversible reaction pairs among three states: the X plus E state, the C state, and the C star state. Now, making all reactions reversible is not sufficient to, it's not the same exactly as a system that's in equilibrium. What you need in addition is you need to ensure that all the forward fluxes along any of those reversible reactions are the same as the backward fluxes. Okay? So that is to say that, Fxe is the same as Bc, and Wc is the same as Zc star, and Fxe is the same as Bc star. Okay? These ensure that there's no sort of bias in this triangular cycle in one direction or the other. And that's what an equilibrium system is. It's sort of exploring a space without any sort of flow. Okay? In this particular example, we can immediately see, because I've made things easy with the rates, that this equation and this equation imply that C equals C star. And if C equals C star, then even though the rate of product formation is dependent on C star, it will be equal to that of C, and we'll be back to the original situation. Okay, so we'll only have the original error, not the squared error. Okay, so the main point I want to make is that by making these reactions reversible, we introduce a flux in this triangular state space, going from with much higher preference from C to C star, and from C star back to X plus E. Right? So there's a flux in this state space. And that's not there by definition in an equilibrium process. Okay, is that clear to everybody? That's just, for most of you, it's a review, but it's something I wanted to keep in mind when we now talk about the thermodynamics of cell sensing. Okay. So like I said, this is a very active field, and I'm going to follow a recent paper, relatively recent paper, by Pankaj Mehta and, as promised, the absent David Schwab. I think this is from 2012? Okay. And the task or the problem that they considered was the following. So they imagined, first of all, they really boiled things down, and they imagined a cell, and more specifically, they imagined a single receptor on that cell. Okay? And once again, they imagined a uniform background concentration, C naught, just like the Bergen-Purcell problem. And ligand molecules can bind that receptor at a rate alpha. They can unbind that receptor at a rate mu. Okay? And then, in principle, this is all equilibrium, right? So we haven't actually introduced any non-equilibrium processes. Diffusion is an equilibrium process. Binding and unbinding of a receptor is a reversible reaction, and so that's an equilibrium process. But the argument was that, usually what happens is that a cell wants to do something with that information in the interior, right? So it needs to initiate it, or it very often initiates some sort of internal signaling cascade. So we want to include that in the model, and we're going to do that in the simplest possible way. And so we assume that if the receptor is bound, then it produces some internal molecule, and that molecule can also degrade. And so we can call that production rate beta and that degradation rate nu. They also, for the sake of completeness, right, this is happening at propensity mu, it's unbinding, and then at a propensity alpha C naught, it's binding. They also allowed unbound receptors to produce internal molecule as well, so long as the rate at which that happens, beta naught, is less than the rate at which it does when the receptor is bound. Otherwise, it doesn't make any sense, right? Then the production is not coupled to the sensing. So I can call this now beta 1 and beta naught, and the point is that if I define delta as beta 1 minus beta naught, that's greater than or in principle equal to 0. And we can say that the degradation rate is irrespective of how it was produced. Okay? So actually, strictly speaking, this is not just for completeness. We'll see that it's sort of necessary in order to get a thermodynamically well-posed problem. Okay? Now, this part, as I said, is perfectly fine in terms of energy because it's just an equilibrium reaction. But this part, these are, completely irreversible reactions, right? The way in which a molecule is produced is not reversible by the way in which it degrades, right? So we should expect some sort of non-equilibrium character to this that we ought to be able to quantify in terms of how much energy is dissipated as this process goes along. And the goal here is to relate that, or at least to have in both of our hands, an expression for how good the sensing is in terms of error that we've been talking about this whole time, and how much energy is dissipated. And we ought to be able to ask whether they're related. Does it always require energy to sense well? How much energy does it require, et cetera, et cetera. Okay? So that's the plan. All right. Now, if we were to approach this problem the same way that we have been in these lectures, then we would do the following. We would say, okay, let's write down dynamics, let's put noise on those dynamics, and let's go from there. And the dynamics would look something like C dot equals d del squared C. We only have one receptor in this problem. We can assume it's at the origin. We can prescribe a delta function to indicate that it's localized. In principle, it has some length scale, which I usually have been calling S, and we can put that back in if we go to Fourier space, et cetera, et cetera. The source and sink nature will be described by some binding variable, right? So let's say when it's bound, B is 1. When it's unbound, B is 0. And so the dynamics of B are alpha times C times 1 minus B. So this says that the receptor can be bound if it is currently unbound, and it's bound with a propensity proportional to the concentration. And it can unbind given that it's bound. And then we can, call the number of internal messenger molecules M. And so we have M is created at rate beta naught from the unbound receptor, and it's created at rate beta 1 from the bound receptor, and it's degraded with rate nu, so propensity nu times M. And we add noise as before. Okay. Look good? Anybody have any problems with this? Why didn't I ask that before? I've been doing this for like 4 lectures. Is there anything different about the model I've written down here compared to some of the things I've written down before? We already worked this one out in therapy. So hopefully you should have no more problems with adding noise to a diffusion equation, which some people already call noisy or probabilistic. Mike?
Why are you describing the state of a receptor by like a differential equation? It's a binary variable.
Yeah. Yeah, that's what I was looking for, right? Langevin equations are usually used to describe continuous variables, actually. They're sort of, they're designed that way by construction. And something I haven't mentioned explicitly is that we've been using those to describe variables which of course are discrete, like molecule numbers, this whole time. That's generally okay if molecule numbers are pretty big, because the size of the noise goes like the square root of that molecule number, and so the noise becomes much smaller than the molecule number itself if the molecule number is big. This molecule number for the binding state of the receptor is not big, right? It goes from 0 to 1. And in fact, it can only take the values 0 and 1. And so describing it as a continuous variable that can go between 0 and 1, I guess, and adding some continuous noise is patently ridiculous, okay? And this is not one of those situations where I'm going to say, well, we're going to do it anyway and everything's going to be fine, okay? This actually will give you wrong answers. Yes?
Could it be the case, though, that like the often non-binding rate is so fast that like in a given time interval we can think of it as being some number between 0 and 1 that describes the...
That's a very good point. That is a very good point. That is a very good point. So, okay, one cop-out answer to that is I don't want to make that assumption. Let's derive something general, and then we can maybe look later at whether that matters. But somehow I have a sense that it still will be problematic, and I can't quite articulate why. But let me tell you a story, and then that might help, right? So, anyway, the point is that this question of essentially how to correctly calculate the noise in the binding and unbinding to a receptor, it started with Berg and Purcell. It got sort of reinvigorated with many people over the past 10 or 15 years, and it's sort of caused a lot of pain, and I feel like there's many ways to approach this problem that are not this way, and you can do it better, and I don't want to do that today, but I do want to tell you what the result is, okay? Okay, so what I'm going to do is I'm going to tell you the answer that you get if you do this part better. I mean, this part's fine if we assume M is large. This part's fine if we assume the concentration is large. But to do this better, by the way, one of the options is to essentially go deep down a rabbit hole of reaction diffusion theory, right? And sort of think on a single molecule basis of the probability of that molecule being in space and time, and account for the probability that when it leaves the receptor it rebinds, or maybe it rejoins the bulk or something like this. But the irony is that if you do this all very well, you get something that's basically what Berg and Purcell kind of just got in the first place. They just sort of wrote it down smartly, and so in the end, this is wrong, but there are many ways to do it right. That's the point I want to make. Okay. So, what do you get when you do the right answer? Oh, before we talk about that, there's another issue here that is much simpler to resolve, but it's just something we haven't addressed yet. And that is the following. So because I have explicitly, accounted for receptor binding and unbinding and therefore saturation. I mean saturation at 1, essentially. This is still a linear model, so there's nothing wrong there, but it is one in which the readout is no longer strictly proportional to the thing that's trying to be sensed. Okay? So to be specific, the mean sort of binding occupancy is, of course, alpha C naught over alpha C naught plus mu, the binding propensity over the sum of the propensities. And then, you can see from here that the mean number of messenger molecules is, see, I'm too lazy to do algebra on the fly, is B bar times this thing I defined as delta, that's just the difference of the betas, plus beta naught over nu, right? And the point I want to make here is that you can see already that M is not strictly proportional to B bar because it's got this constant, and moreover, B bar is certainly not proportional to C naught, right? So that is to say, we can't just say that the error, which we were thinking of as sort of the estimate, or the error in the estimate of C, that's not strictly equal to the variance in the long time average of M over M squared. Instead, we have some transformation factor due to the functional relationships here, right? And I can motivate that factor fairly straightforwardly, and that will ensure that we're doing a proper estimate. Right, so the point is that, if you just think of this like error propagation, right? A small fluctuation in M should be related to a small fluctuation in C via the derivative dm dc, or more specifically, the derivative of the mean functional relationship evaluated at the mean of C. And so we should expect that the variance obeys a similar type of relationship, right? Except with the square of the derivative. Right, so all of that is to say that to get these factors right, we now have an error estimate that is almost what we've been thinking about when things were proportional, but times a factor which I can write as M bar over C naught times dm bar dc evaluated at C naught squared. And I hope it's clear that if M bar were proportional to C naught, then this would just evaluate to 1. Right? Those are the situations we've been in so far. Here we need to be a little bit more careful. Okay? But all of these things are calculable, obviously. M bar is related to B bar is related to C naught, and the variance in the long time average is obtainable with some caveats using a method like this by going to Fourier space, or if you're more careful, you remove those caveats. And I just want to sort of give you the final expression. So the final expression has 3 terms. It has a term that looks hearteningly familiar as sort of a Berg-Purcell-like term. It has a term that looks like 1 over the unbinding rate times time times the mean occupancy. and it has a term that looks like 1 over the degradation rate times time times the mean messenger molecule number, or internal molecule number, times an additional factor, which is m bar over b times 1 minus b times nu over delta quantity squared. And I think I forgot some 2's, but those don't, that's not really what we're interested in here. Okay, so how do we interpret this? So this is the noise from counting the molecules that bind the receptor. This is the kind of thing we've been talking about most often. It's the noise that I called extrinsic last time. And it's just it involves counting the molecules. This is noise that arises from the binding and unbinding kinetics of the signal molecules to the receptor itself, right? When that molecule unbinds is a stochastic event, right? And so the fact that that's involved in this process is adding additional noise to the problem. And finally, this is the noise involved in the production and the degradation of the internal molecule. Right? So together these are sort of called the intrinsic noise. And they have a similar form, right? They're sort of like the intrinsic timescale, or the intrinsic rate times the timescale. That gives sort of the effective number of independent measurements times the mean that you would expect from a sort of Poisson process. Except there's a little bit of mixing here, right? In the sense that there, a 1 minus b bar pops up in here, some b bars pop up here. There's like a delta thing here. And these are the kind of things that you might that I was talking about that sort of go haywire when you do this, but they need to be here for physics, I think, because we can think about certain limits that need to be true, right? So, and by the way, these first 2 terms are sort of what I addressed in the first lecture when somebody asked, oh, what about binding kinetics? Oh, what about when it's just the receptor? So, what are those limits, right? So, if the receptor is never bound, then nothing is sensed, and we should expect this to go to infinity, right? That would be b equals 0. Well, indeed, this blows up, we're good. If the receptor is always bound, well, then it's completely saturated. It can't sense anything new. B is 1, this blows up, we're good. Any other limits that are comforting about this expression? Sorry? When t is large, the error goes down, absolutely. This thing sort of goes down with t, as we've always seen. For those of you that might have thought it was weird that I allowed the unbound receptor to also produce molecules, right? I made the comment that if beta naught and beta 1 were the same, then of course this is a useless sensor. Is that true here? Yeah, I would argue it is, right? Because that's this delta, and if delta goes to 0, we also have no sensory capabilities, and accordingly, the error also blows up via this term, right? So, okay, so this has the proper limits, and we're sort of done with part 1 of the problem, which is, what's the error in sensing? Part 2 is the sort of more interesting part, which is what's the energy dissipated in the sensory process. And this quantifying the energy dissipated in chemical reactions is an entire field in and of itself, and there are many fundamental results, and I just want to quote one for our purposes. And it holds for any sort of set of Markovian reactions. and it's a result that gives the so-called entropy production rate. And the idea is that when you have flux cycles, like I've described, and you're driving your system out of equilibrium, then you're necessarily producing entropy, and Kb times that entropy is essentially the energy that you are dissipating as heat into the environment, right? This is a real thing. It's, you know, if we were really careful and technically gifted, we could measure it, you know, on a molecule by molecule basis as things reacted inside of cells. We could hold a thermometer out. That's not how you do it, but you know what I mean. So the entropy production rate in general has a very simple form. It's the sum over all states of your system and all states you could transition to of the probability of those states times the transition rate from one set of states to the other, you know, one state to the other state, times the log of the ratio of the forward transition, again, over the backward transition. Okay? Looks a lot like entropy, right? You definitely have like a P log P feel going on there. I'm not going to sort of prove this or anything. I'm just going to take it at face value and specialize it to our reactions with their own transition rates so that we can get an expression for our system for how much entropy is produced. So in our system, we have sort of two things that govern the states. We have B and M. And we have essentially 6 reactions that can take place. We have, if B is 0, then M can go to M plus 1. If B is 1, the same thing can happen. These are the rates beta naught and beta 1. If B is 0, M can go to M minus 1. Or if it's 1, and those are the rates or the propensities nu times M. And finally, for any M, B can go from 0 to 1, and that's binding, and that's happening at alpha C naught, or it can go from 1 to 0, and that happens at rate mu, right? So that means we're going to have 6 terms in this expression. And they're going to look like the sum over M. We have P0M, right? This is our probability of PBM times beta naught log of beta naught over the back reaction, right? So the way to think about this is if M goes to M plus 1, that happens at rate beta naught. If you start then at M plus 1 and you need to go backwards, that happens with propensity nu M plus 1. Okay. Or you could be in state P1M, and the same thing could happen with rate beta 1. Okay. Or you could be in state P0M, and you could have a decay, which could occur with propensity nu M. And now you've gone from M to N minus 1. The back reaction is now bringing you back to M, and that happens with rate beta naught. So this looks like nu M over beta naught. Or you could have the same thing happen with the bound receptor with rate nu M again, but the back reaction would occur with rate beta 1. And then we have reactions 5 and 6, right? You can be in the unbound state, you can have a binding event, and the back reaction is an unbinding event, or you can be in the bound state, you can have an unbinding event, and the back reaction is a binding event. Okay? So, I don't want to say too much about this except for one important point. There's something special about these last two terms. What is it? They don't depend on m, so I can absolutely sum through the m here, and I would get something like the probability marginalized over m that that the receptor is bound times AC naught. And actually, I might as well factor out this log because it's the same apart from a minus sign. So the last two terms look something like this. Anything else? They die. They die in the name of detailed balance. Right? So this is the probability being bound times the propensity to, being unbound times the propensity of getting bound. This is being bound and then getting unbound. If receptor binding is an equilibrium reaction, this is the statement of detailed balance, that these balance each other. Right? And that, in turn, is the statement that that part of the scheme is in equilibrium. These terms don't die. And that is the statement that the other part is not in equilibrium. We get a finite entropy production rate. And now we come to the end of the story. Because I'm not going to, this is brutally ugly. This is we rely on David Schwab for this. that you can solve the master equation, you can get the answer for the steady state distribution, you can plug this in. But I will show you what a plot looks like. Because this is ultimately the question we care about. We care about, as a function of, say, this delta, we just found earlier that the error blows up, and then it reaches some noise floor, but it blows up as delta goes to 0. If you plot this expression against the very same parameter, you find that it goes to 0 as delta goes to 0. And this is the statement that sensing requires energy dissipation. In other words, unless you're okay with sensing with infinite error, which is essentially sensing nothing, in that case you have no energy dissipation. But anything else requires finite energy dissipation. So it's in this example, it's kind of easy to see. You need a different production rate with or without the receptor bound. But the point here is that any sort of discrimination of that, which will tell you the ultimate outside concentration, requires you to drive your system out of equilibrium. Ilya.
So have always been confused about this result, and the confusion is the following, right? So if the sensor, if the concentration is there and it's unknown, it must be changing, right? Maybe very slowly, but nonetheless it must be changing. And so if it's changing, then it's a changing chemical.
What is changing? Sorry?
Over time it has to be changing, otherwise
what is it? Sorry.
The concentration, the external concentration.
The external concentration, sure.
If it's changing, then the chemical potential is changing. I can couple to that, and I can use that to drive any kind of sensing I want. So think of a situation where I have basically a turbine inside the cell wall, which lets molecules in, and as
okay.
change,
So now you're yeah.
The tidal power plant.
Okay.
Right? And then it flows out, and you're running it again.
So I'm going to call that a demon.
No, Because there is a
Right?
There is
So-
a change in the chemical potential because the concentration has changed outside. I'm coupling to it. I'm not.
Okay.
I'm using the external energy. I'm just not. I'm smart to not use my own.
So let me start the answer to that question by, again, I'm like really anal about this. I want to be respectful of your time. But as you can tell, the thermodynamics of chemical reactions is a hot topic, and I only work on it a little bit, but let me end there and just say, thanks for your attention. Now, so your question, it's sort of my knee-jerk reaction is are you exploiting some sort of information about which fluctuations go up and which fluctuations go down to do something different within your cell with that information? And of course, that's a fundamental question that is sort of a seed at the heart of this field of the relationship between not only sensing and thermodynamics, but also information and thermodynamics. You say that's not a demon, so why is it not a demon?
I mean, it's the same situation if I have two reservoirs, one inside the cell, one outside the cell. I'm trying to measure how, just think of water reservoirs. How much water is in the water reservoir, how much higher it is than what I have in the cell. So I put a turbine and let the water run.
So,
and the faster it rotates, the larger
oh,
it
okay, I
rotates,
see.
right?
So you want to exploit some sort of existing concentration difference or water difference or energy difference.
If I have to measure concentration of something outside
Yeah.
the cell,
So
then
maybe the
it's-
counter argument is, can you do what you're describing cyclically?
Yes.
Why?
Because the concentration keeps changing. I think the argument is
Okay.
changing.
Okay.
I think the argument is not that you don't have to expend energy or something. It's just that you can draw that energy from the
Yeah.
environment.
So then the task might be different. In other words, this task that you're claiming is energy free or something might be a fluctuation detector, where you're actually interested in information about the fluctuations, as opposed to averaging them out somehow. In other words, I might believe that the latter requires energy, whereas the former does not.
I disagree.
Okay. All right. Let's take that offline. Okay. Anything else? I mean, as you can tell, it's not a resolved topic, and I believe at least one of your projects is on that. So this will continue this afternoon. Okay. Thanks again.